Hello, welcome to my talk on the simulation of the position supremum and the time of the supremum of a Levy process using a stick-breaking Gaussian approximation. This is joint work with Jorge González Casares, who is also at Warwick and the Turing Institute. Okay, so we're interested in, given a trajectory of a Levy process on a fixed interval 0t, we want to know about the law of the three-dimensional vector consisting of the position at time capital T, the supremum at time accumulated by time capital T, and the time this supremum was attained. This kind of triplet crops up in many settings in applied probability, including mathematical finance, for example, risk measures like drawdown and the duration of drawdown for exponential Levy models. Now, I want to study a general problem for all Levy processing, a general method, and that's going to be stick-breaking approximation method. So in order to introduce it, I need to remind you quickly what the stick-breaking process is. That's a thing which is independent of the Levy process, and it partitions the interval, the time interval, from 0 to capital T in a simple way. It starts at capital T, and then you sample a uniform between 0 and capital T, say capital L1, and the first stick length is little l1. And then you repeat this procedure on a smaller interval from 0 to l1. Recursively. So you can see in this picture, after 4 steps, the interval that's left is very small from 0 to L4, and that's no coincidence because the expected length of the interval is decaying geometrically, and that's an important feature of all that follows. Okay, so our method is based on our previous joint work with Geronimo Uribe Bravo, which produced a coupling between x and y, where y has the same law as the Levy process, the same law as x, and the coupling is independent of L. And using this coupling, we get an almost sure representation for the vector of interest. Okay, so it's a sum of over a few stick lengths of the increments of y plus an error, where error has the same form as the original triplet, except that it applies to the law of the process over the interval from 0 to ln, over a very short interval. So this will be geometrically small, typically. This guy here will take up most of the action and is a very simple function of the increments of the process y over the stick-breaking lengths. Okay, so for example, for the supremum, I just need to add up the positive parts of these increments, a few increments, I think 10 or something like that. And no maximum for the time of the supremum. I just add up the stick lengths where the increments were positive. Right? So Geronimo is going to give a talk on this in the applied probability session. If you need information about this triplet, that's the only geometrically decaying algorithm that does that for you, and consequently its computational complexity is optimal up to log factors. The thing that it does require is the ability to sample these increments of y or of x for a fixed time. And that is a non-trivial thing for the following reason. Right, so recall, I mean, XLA process got this triplet. There's a Brownian component here. There's a Brownian component. It might be 0. Nu is a Levy measure. It's always non-zero. If you're studying Levy processes, not trivial Levy processes, and B is drift, and it's Levy to the composition of X. Is a bunch of processes that I can sample increments of. Remember, I'm after increments now, right? So I've got Brownian motion with drift, no problem with increments. I've got compound Poisson component, J2 kappa, and that's no problem with increments in principle also. And I've got this guy here, which is a pure jump Levy martingale consisting of all the small jumps of x, smaller than kappa. And this law is completely intractable for simulation purposes typically. Okay, so this problem is a general problem. It's been addressed by now classical paper by Asmussen and Rosiński, who proposed the Gaussian approximation. So that's my Levy to the composition of x. What am I going to do? Well, this guy is an L2 martingale. It's got a variance. You see, variance expressed in terms of the Levy measure as an interval minus kappa to kappa, where x squared mu dx. This goes to 0 as kappa goes to 0. But so it's got this variance, and now I'm going to substitute this martingale with this variance with a Gaussian martingale, another independent Gaussian martingale. Now, what is this process? That's my Gaussian approximation process, and that guy has increment that I can sample. Right? I can sample it. How? Well, you see, one thing I can do is I can sample the jumps of the compound Poisson process, and between the jumps, I just have a Brownian motion with drift. I can sample the increment and say the supremum of that over that interval, and then do this, do the sequential sums and compute the maximum over each of them, and then obtain the value of this statistic. So in principle, this can be done exactly. However, this is numerically unstable, particularly when kappa goes to infinity, kappa goes to 0, when in the non-trivial case when x is infinite activity. The reason is that you're adding large quantities of very small numbers that due to rounding are forgotten, and then you're sequentially doing that, which is fine, but looking at partial sums and then computing minima and maxima leads to instabilities and non-convergent algorithms. This problem doesn't occur for the marginals, which is important because there you're just adding, so the small errors that you make don't result in big discrepancies. Okay, so what I want an algorithm where I can sample this statistic better, so I can sample it in a stable and fast way, and then once I have such an algorithm, then I want to know, what the Wasserstein distance is between the actual statistic and the statistic that I can sample. And also, can I do multi-level? Can I produce a coupling between two different levels? So that's what my talk is about. And so our main idea is to apply the stick-breaking approximation to the Gaussian approximation, right? So because stick-breaking approximation holds for all Levy processes, I can apply it here. I get exactly the same representation as before, right? Now all these increments are sampleable because they're the increments of the Gaussian approximation. But now I can also sample this guy. I can also sample the remainder exactly using the algorithm on the previous page, because the interval ln, you see the length of the final stick is going to be very small because it's geometrically decaying. So the numerical instability will not kick in, and I don't need to use even very big n to do this. Now the key observation, as always in these things, is that most of the stuff happens in the first few increments, right? That gives me most information about the thing that I'm interested in. Okay. Now, how am I going to compare the laws? Right? So I need a coupling. I need to devise a good coupling between the Levy process and its Gaussian approximation that sort of respects this stick-breaking structure. Okay? So because the stick-breaking process itself is independent of the Levy process, I can use the same stick-breaking process for the approximation, to the Gaussian approximation, and for x. Then I can use the minimal transport coupling for the increments over the sticks for each of these guys, right? So this is the y that appeared earlier for x kappa, and this is y that appeared for x. Okay. Right. And then I use the SBA coupling for my second slide to link y to x and y kappa to x kappa, and this gives me the right coupling that will produce the following theorem, right? So this is the theorem that there's the bound and the bias. Okay? So there are some universal constants, k1, k2, and this coupling, and now I look first at the distance between the positions at the final time and the suprema at the final time. I look at the L2 thing in this specific case, and the bound is of this type. You see there's some logarithmic correction, which is not important, and it's the minimum of two things, right? So this is the thing that depends on time, and it depends on time horizon, and describes the sigma. It comes from the independence coupling. So here is the guy that actually drives the rate typically, and here you see if I have a Gaussian component, I have very good rate because I have a rate which is kappa times sigma bar kappa. Okay? I can obtain a similar bound for the laws of the times of the supremum. See, these things are quite singular, right? Time of a supremum is typically not a continuous function of the trajectory, right? And yet the laws are very close, and in particular, there is a Brownian component. The laws are very close because they're kappa over sigma bar times sigma bar kappa squared. See, this goes to zero very fast. Remember, this is the variance of my pure jump martingale J1 kappa. Okay. So this theorem holds for all Levy processes. It's bounds and always bounds for all the P. Dependence on time horizon is explicit, which is would be important in certain applications, not just explicit constants, implicit constants. And also I need to say that the coupling from before, I need to also, in order to prove this theorem, I need, particularly for the time of the supremum, I need to consider also problems to do with the Kolmogorov distance, which I don't have time to go to in this talk. Okay, we need a bound. Okay, so what's the inspiration? What's in the literature? So Mariucci and Rice had a coupling for the marginals between X and its Gaussian approximation of this type. And this is actually the first thing that we started using until we realized that we could slightly improve on that in the case when X has a Gaussian component. You see, if the X has a Gaussian component, and the sigma squared is, if sigma squared is 0, our bound, this bound is exactly the same as the Mariucci-Rice bound. But if sigma squared is positive, then this bound is kappa sigma bar kappa squared over P, but P is 2, let's say, then it's kappa sigma bar kappa. So this goes to 0 fast. And this leads to the bound on the Wasserstein distance for the supremum and the position, which is sort of a logarithmic factor away. Okay. Now, I can use this coupling to this idea to extend to a coupling between two Gaussian approximations for different kappas, and that leads to MLMC algorithms. Right? So let me discuss that now briefly. Right? So what are these graphs describing? So x-axis is the Blumenthal-Gatur index, so the activity of the Levy process. Y-axis is the dominant power in the computational complexity of the corresponding Monte Carlo, multi-level Monte Carlo algorithm. It starts at 2 because it's always at least 2. And we're comparing here our results with the results of Derreich and Heidenreich. And you can see they did the case when f is a Lipschitz function, and it always goes up to 6. In our case, it stays bounded by 4, this computational complexity. And of course, we can also do things that are payoffs which are discontinuous because we have control over the Kolmogorov distance. We have done this both both for the supremum and the time of the supremum. So the distribution function of the time of the supremum. These are the numerical results here. Okay, thank you very much for your attention.